Hello fellow engineers, welcome again. And as per our web series which is dealing with front-end system engineering for radio astronomy, we have already covered I think 14 videos so far, and this is our second last video, and the very next video would be the conclusion of the web series. And in this particular video I will be talking about something really different and which we haven't talked before in our earlier videos. But it is related to the front-end system engineering for radio astronomy, and it is mainly related to the circular waveguide filter which we have discussed in our earlier videos to get rid of mobile bands. So actually this video is revisiting the circular waveguide filter for radio astronomy applications in L band, and with a thought in mind, can one do a design which is way compact than a circular waveguide filter and still achieve very low insertion loss for the filter such that it can be used before a low noise amplifier in radio astronomy instrumentation systems. As you have seen in earlier video, the circular waveguide filter was working really fine. It was giving the adequate attenuation to your mobile bands. It was definitely having well matched response during 1.05 GHz to 1.6 GHz bandwidth. The insertion loss was also really low. Since it's just a waveguide filter, there is absolutely no lossy component inside. But it is really bulky and it's really long. It was 800 mm long and is also heavy. So that started me thinking, can I design a filter which is compact and could still achieve similar performance as that of circular waveguide filter? And the answer is yes. I dipped into various different filter topologies which people have already developed, and interdigital filters is one such filter topology with which one could achieve a compact L band filter and with the ability to reject mobile in a really nice manner. So as usual, I have done the EM simulations and then I have done a CAD model, and what you have in front of you is fully fabricated and assembled prototype of new highly compact L band filter which has at least 40 dB rejection to both mobile bands and really low insertion loss from input to output. The insertion loss of this guy is of the order of just 0.15 dB. Is it low loss? Well, if one just say in terms of loss, it's really low insertion loss, 0.15 dB. But if I talk in terms of radio astronomy perspective, usually I would like to have this filter before my low noise amplifier, and then even a 0.1 dB loss matters. So with 0.1 dB to 0.15 dB insertion loss of this guy, this filter would at most add 10 Kelvin to your system noise temperature. If that is tolerable, then one could get rid of really bulky circular waveguide filter and redesign the L band system to make it really compact and still as competitive as that of circular waveguide filter. However, circular waveguide filter does support both the polarizations at the same time, that is two orthogonal ones. But if you use this kind of filter, it naturally supports just one polarization because it has a coaxial connectors on either end. So the system would need two such filters together before two low noise amplifiers for two orthogonal polarizations. Having said that, let's have a look at the simulations of this filter and the measurements. So as you could see on the screen, as usual I have modeled this entire filter in WIPLD Pro, and this filter is of the type interdigital filters. It means it will have some sort of metallic obstruction inside this metallic cavity, and these obstructions are periodic, and by carefully tuning the size of the metallic obstruction and the spacing between these obstructions, one could design a really good bandpass filter. Most of the theory about interdigital filters is available in classic filter microfiltering textbooks or microfiltering handbooks, so I won't go into in detail of that. But what I will try to show you now, the simulated performance of this very filter using WIPLD Pro. So as you could see on the screen now, I have simulated this filter over a fairly wide frequency range, all the way from 800 MHz to 2 GHz. And have a look at the stop band. At the lower side, around 960 MHz or less, the insertion loss of the filter is minus 40 dB and less. The S21 is minus 40 dB and less, while the upper stop band above 1700 MHz is again 40 dB or better attenuation to unwanted mobile bands for radio astronomy applications. While the pass band is fairly flat, the design is for just 0.2 dB to 0.25 dB ripple in the pass band, and the insertion loss of the filter, have a look, is at most, at least as per the simulation, is of the order of 0.1 dB only. So this guy would add at most 7 Kelvin to your system noise temperature, but your system using this filter would be highly compact and very much attractive in terms of mechanical aspects. Also, looking at the S11 or S22 of this particular filter, the matching is minus 12, minus 13 dB and less over the desired band of interest. So definitely this filter could do excellent pass band between 1.05 GHz to 1.6 GHz or so. So these are the simulations, and based upon the EM model and then converting that EM model into mechanical model in Autodesk Fusion, I have done a nice fabrication of this particular filter, which you could see in front of you. And this very filter, these two are exactly the same, exact replicas of each other. I have connected one with the network analyzer to have a look at its S parameters. So now let's have a look at S parameters of this fabricated filter prototype. So now we will have a look at the measurements of this particular filter. But before measuring this filter with a VNA, we have to also have a look at the calibration of the VNA very carefully, because the insertion loss as per our EM simulation of this filter is 0.1 dB and less, and measuring such a small insertion loss requires a really good calibration on the VNA. I have a moderately good calibration, so what I am going to do, I will simply connect the port 1 to port 2 using just using a female adapter and see what sort of S11 and S22 I get in terms of a through cable measurement. So at first I have done a through measurement of these two cables, and the result is already shown on the screen. And as you could see, the S21 is fairly close to 0 dB, but it has some ripple of the order of 0.05 dB or 0.08 dB. So naturally, if I want to measure an insertion loss of just 0.1 dB, I will have some error in my measurement. But at least this gives me an idea how well the calibration of my current setup is. Hopefully that can be improved. But I will leave with this particular through measurement as of now, just to give you an idea what sort of insertion loss this nice metallic cavity based filters could give using interdigital technology. So now I have connected the filter again between port 1 and port 2 of the VNA, and the result I will show you on the screen now. And as you could see, the insertion loss is of the order of 0.18, 0.15 dB or so. Also the passband looks fairly close to what we have simulated. The stop band rejection, one of the important feature of this filter. And as you could see, the very first marker around 960 MHz, the measured attenuation by this filter is minus 40 dB, very close to our simulated value, which was about minus 41, minus 41.5 dB. The upper side, the fifth marker, which is at 1710 MHz, has definitely minus 42, minus 43 dB attenuation, and the matching of the filter between 1 GHz, 1.05 GHz to 1.6 GHz is all the way below minus 13, minus 14 dB, and the last feature, that is the insertion loss, is just of the order of 0.15 dB, considering the complete fabricated prototype with realistic connectors attached to it. So this filter, I believe, is a really good design for doing L-band radio astronomy observations in a city-like noisy environment where you have mobile all around present with a potential situation to saturate your low noise amplifiers. This could solve the problem in a really compact manner and with very low insertion loss. So hopefully the next version of Tantrayud's L-band radio astronomy system, front-end system, would come with this type of filters, and the entire system would be really compact in a size of say 60 centimeter by 60 centimeter by 60 centimeter. And that's a really good feature with the system. So with this, actually we have covered most of the RF front-end parts of radio astronomy instrumentation or the front-end system for radio astronomy. And the next video, which is our very last video of this web series, I will try to cover the overall system aspects and how this system would perform in terms of practical numbers in a prime focus reflector. So till then, see you, goodbye.